Hi guys, welcome to again to my channel. My name is Mallasa, and today I'm gonna be show you the design of foundation in high-rise building based on Eurocode and Ethiopian building code of standard. In the previous tutorial, I have already shown you the detailed punching design of slabs and foundation. And today we'll see the tutorial part 28, which will be focusing on the detailed designing of foundation in high-rise building based on the European Building Code of Standard and Ethiopian Building Code of Standard. So this tutorial will be focusing on the design of a shallow and deep foundation. If you are a new member for this channel, don't forget to subscribe my channel. If you subscribe my channel, you will be getting a more relevant tutorials, so which have already been prepared with reference to the detailed modeling analysis and designing of a 20-story building based on the Ethiopian and European building code of standard. And if you are a member of my channel also, don't forget sharing all my tutorials to your friends so that your friends will be getting more relevant tutorials which have already been prepared based on the detailed designing of building and steel structure based on the European and Ethiopian building code of standard. If you wanted to receive an immediate notification for the newly uploaded video, you can press the bell icon. And if you have also comments and questions regarding to the designing of any civil engineering projects, you are always welcome and provide me comments in my commenting box so that I will be answering your questions as much as possible within a short period of time. So, if you want to get more tutorials that have already been prepared by the Global Structure Design and Construction Solution, you can visit my YouTube channel. So here, just this is the channel. Just simply write the Global Structure Design and Construction Solutions on the search bars of your browser, so that your browser will be leading you to the links of the my channel, which is the Global Structure Design and Construction Solution. And just you can just click on the link. You'll be getting different types of tutorials that have already been prepared by the Global Structure Design and Construction Solution channel. So just you can here just when you are just directed to this channel, you can press this button, the video button, so that all the prepared videos will be displayed here. Here, starting from here, this is the previous tutorial, and there are all the recent tutorials are listed at the top, and the oldest tutorials will be listed at the bottom here. So you can get the tutorials which have already been prepared with reference to the detailed designing of steel structures based on the Ethiopian and European Building Code of Standard. Here, this is the steel warehouse. The starting from the modeling up to the designing of connections, where just perform it based on this steel structure here. Just you can get more informations and knowledge for the designing of steel connections. Even here, steel connection using the Autodesk Robot Structural Analysis Professional and steel connection based on the idea statica. So, and even you can get also tutorials which is prepared based on the modeling and the designing of reinforced concrete reservoir. And here the also the analysis and designing of this journey story building. Also here listed all the detailed tutorials that have already been prepared uh, in the previous session. Just you can get here. So let's proceed to the today's tutorials, which is tutorial part 28, which will be focusing on the detailed designing of foundation in high-rise building based on the European and Ethiopian Building Code of Standard for the shallow and deep foundation. So the here we will have contents. The contents comprises different types of content here. The first one will be the fundamental concepts in foundation, and the second one will be the types of foundation, which are the shallow foundations and the deeper foundations. The third one will be focusing on the soil pressure under foundation. These are the gross soil pressure and the net soil pressure. And the fourth one will be focusing on the distribution of soil pressure under the foundation. So let's proceed the detailed parts of those contents one by one. The first one is the fundamental concepts in foundation. So, what is foundation and why we use the foundation in high-rise building. So, foundation is nothing but it is the lowest part of the building or the civil structure that is in direct contact with the soil, which transfers loads from the structure to the soil. So, here, suppose we'll have the superstructure here. We may have a superstructure here. So this is the ground level here. That is the NGL here, and this is the top level of the building. So here the part which is located below the natural ground level, what we got is the foundation. So the foundation is nothing but it is the lowest parts of the civil structure that is in direct contact with the soil and transfers the load from the superstructure and carries the load which is coming from the superstructure. So this what we call it is the foundation. So, generally, the foundation can be classified into two categories, namely, that is the shallow foundation and the deep foundation. So, what does the shallow foundation mean and what does the deep foundation mean? So, we'll see next. So, the foundation that is placed near the surface of the earth or transfers the load at a shallow depth is called, it is the shallow foundation. So, here, suppose this building is, it is, the low-rise building, suppose. If it is a low-rise building, if it is low-rise building, so it will have, that is a small structural load. That is small structural load. So, for a structure having a small structural load, we will be using the shallow foundation. So, shallow foundation is nothing but it is placed near the surface of the earth. Here, this is the surface of the earth. So, we'll go down. So, the depth of the foundation will not be that much higher. So, it is up to maximum of 3 meter. So, the foundation that carries the small structural load coming from the low-rise structural parts of the building, what you call it is the shallow foundation. So, foundation that is placed near the surface of the earth or transfers the loads at a shallow depth is called the shallow foundation. So shallow foundation is cheaper. The shallow foundation is cheaper and easier to construct. So when we say it is cheaper, it uses the labor for the execution of the foundation. And it is also easier because we will not be using more mechanized systems, so just like the drilling pile or the shootcrete machine or the anchor machine. So in the case of shallow foundation, we will be using only the labor, and sometimes we may be using some commonly available machines such as excavator and loader. So, shallow foundation transfer loads mostly by endeavoring. So, the foundation is in contact with the surface. Suppose here, this is the structure. So, we may have here an isolated footing here. So the load which is coming from the superstructure, that is the collar load, will be transferred to the sub parts of the soil, that is to the substrata parts of the foundation. So these parts of the foundation which is in contact with the footing will generate this an end bearing. So the load will be transferred by using end bearing systems. But in the case of a deep foundation, we will see later, we may use the side friction method here. We may use side friction method, but in the case of shallow foundation, we will be using the load transferring mechanism, or that is called the end bearing mechanism. So here, that is why just we will be using end bearing system of load transferring mechanism. So the shallow foundation transfer load mostly by end bearing. There will be a possibility of settlement, usually applicable for light water. That means there will be a possibility of settlement when we will be using this shallow foundation for higher structural loads. So we need to use the shallow foundation for lower structural loads. That means for lightweight structures. And it is weak against the lateral load. That is why there is a problem of lateral instability when we use shallow foundation. So so some parts of or some examples of shallow foundations are an isolated footing, mat foundation, the strip foundation, the strap foundation, combined footing foundation, and the strap foundation. All those are an examples of the shallow foundation, which are basically recommended for low-rise building or building having low structural loads. The foundation that is placed at a greater depth or transfers the load to a deep strata is called it is deep foundation. So previously, in the case of shallow foundation, we will be using the shallow foundation for uh, the low-rise building or for building having low structural loads. But in the case of high-rise building having higher structural loads, we will be using a deep foundation which enables the structure have higher resistance for lateral loads and also higher resistance for gravity loads. We will place our foundation at a greater depth of the soil in order to get a good strata to withstand the higher structural loads coming from the superstructures and which coming from the just of from the lateral loads such as from wind and from seismic. So deep foundation are really on both in the brink, and that is a skin friction, meaning here suppose we may have the pile foundation just like this. Suppose this is a pile foundation, and here suppose if we have a building here, so all those are the building, all those are those are the columns. So this is piles, for example, these piles which carries the load coming from the superstructure, that means the higher structural loads, and the load coming from the superstructure will be transferred to the soil through the piles. Here we'll have a soil here. So here this part, what we call that is the index of the pile, which is index of pile. So the index of the pile induces indifferent here. That is indifferent. This part is an indifferent. So the mechanism by which the higher structural loads coming from the superstructures transferred to the soil via the end bring mechanism, and also using the side friction. Here we'll have a friction. So the load will be resisted by the side friction as well as by using end bearing. So we'll be using two mechanisms. One is by using side friction and the other is by using end bearing. So the load which is coming from the superstructure will be resisted, that is Q, which is the capacity of the pile, which is equal to the skin frictional resistance of the pile here plus the indifferent capacity of the pile here, that is QP. This is the capacity of the pile. So the capacity of the pile should not be exceeded by the column load coming from the superstructure. So we will be just discussing more in detail while we will be discussing about the pile foundations. Here, there are also some examples of the shallow foundations, and this is the three-dimensional arrangements of a given foundations of a building. Here, this comprises so many types of shallow foundation. When we see this one, here we have a wall here. It may be a retaining wall or it may be shear wall. So the wall will be, carried by the strip foundation. Here, this is a strip foundation, and this one is an isolated footing foundation. And here we have also a combination of two strip foundation here, which carry load coming from the shear wall or the core wall. And in similar way, also here we have a core wall here. The core wall is it is supported by a small mat here. And the other is here we have here we have the strap footing here. This is the properties of or suppose this one is the properties of our building. The all the columns closer to the property lines are placed at the line of the property. Here we have a footing here. So this footing cannot be extended beyond the line of property here. So the column is it is placed at the edges of the footing here. So there is higher eccentricity problem here. So in order to avoid the effects of moment coming from the due to the eccentricity, so we need to provide a strap beam here. So this strap beam will be connected to the the nearby interior footing here, just like this. So the eccentricity problem can be controlled easily. And the other types of foundation is here we have a strip foundation here, also even here, just like this. And here we have also a combined footing foundation, which is the foundation which carries, load coming from two column. So this what we call it is the combined footing. So simply this figure describes the lists of the shallow foundation in three-dimensional configuration. And the first kinds of shallow foundation is spirit foundation. So spirit foundation is nothing but it is a pad and a strip footing used under columns and walls respectively, meaning So these types of foundation can be used for walls and as well as for you know highly spaced columns. So the first spirit foundation is it is a strip or footing is a continuous footing used under walls or closely spaced columns. So like this. And the second one is it is pad footing foundation, which is used to support single column spaced relatively at long distance. Here, this is the example of a strip footing foundation. Here, we have a wall here. This wall may be retaining or it may be shear or it may be core wall. So, this is it is a strip foundation. So, this strip foundation they have a strip a beam here just that you brace these columns and these columns because here if we see the columns arrangements of the column here the column is located at the edges of the strip footing here and this column is also located at the edges of this strip footing. So we need to use a strap beam here. This is what you call this strap beam. So this kind of footing it is a combination of a strap and a strip footing. And the second one is it is pad footing foundation, which is basically used for highly spaced columns having a lot structural loads. Here, suppose here we have a column here, and here we have also an isolated footing here. So the geometry of this isolated footing may be it is slanted just like this, or it may be stepped just like this. So it depends on the contact area and the soil bearing capacity of the foundations. And the other types of shallow foundation is it is a combined footings. Combined footings are used when two columns are so close that single footing cannot be used, or when one column is located at or near property line. Meaning, here suppose we may have a column here, so we may have just a column here. So if we wanted to provide an isolator footing for every column, so just there may be an overlapping of footing due to the limitation of space here. So whenever there is a condition where we will not be using an isolated footing, so we need to provide a combined footing just like this. So combined footing is nothing but it is applicable for columns that are located closely or whenever there is a condition that will not allow us to use an isolated footing. Here, this is some example of here. This is the some of the example of a combined footing here. We have a column here. Suppose we may have a column load here P1, and here we may have also the other columnar load which is P2 coming from the superstructure here. So there is some edge distance here. There is some edge distance here. This is for the case of rectangular footing. That is a rectangular combined footing. That means the magnitude of the column load, that is P1, is approximately which is equal to the magnitude of P2. So in this case, it is recommended to use the rectangular footing or the square footing. But if the magnitude of the load, that means if P1 is significantly higher than that is P2, There will be higher stress here under the column 1. So in order to withstand this higher soil pressure which will be induced under the column 1, so we need to provide higher contact area under the column 1 that is under P1. So in this case, we need to use the trapezoidal footing here, just like this. So just like this. So this is the way how can we provide the rectangular the rectangular footing for columns that are spaced closely, having significantly variable axial loads. And the third types of shallow foundation is a cantilever footing. So in the case of cantilever footing, we need to use a strap beam to connect an eccentrically loaded column and foundation to the foundation of an interior column that we have already seen it. So the cantilever footing is nothing but it is a strap footing, which is a combination of an isolated footing and strap beam, basically used for a condition when there is a problem of eccentricity. Here, this is the examples. Suppose here, this column is located. Suppose here, just like this. That means at the edges of the property line. Here, this is the suppose this property line of the building. So it is impossible to extend the footing beyond the property line because this boundary is only by others person, and the property which is owned by the owner of the building is starting from here up to some boundary here. So this is the maximum length of or width of the building, suppose. In this case, we need to provide a strap beam in order to just tie these highly eccentrically loaded columns to the interior columns. Here, support this is the interior columns. That is support this is interior columns, and here this is exterior columns. That is this is exterior columns. So this is just the arrangements of the strap beam or the strap foundation. And the other types of shallow foundations it is the mat or raft foundation, which consists of one slab, usually placed under the entire building area, and supports more than two columns with high structural loads. Meaning, here we may have support. This is the built-up area of the foundation. It is the built-up area. That is support. This is the built-up area, and here we may have columns here, or we may have shear wall here, we may have column 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 here, we may have a shear wall here, just like this. So we may have a column here, we may have a column here, column here. So the load coming from every columns will be supported by one slab, that is this slab. So this kind of foundation is called, it is mat foundation. So mat foundation is applicable where there is higher structural loads which is coming from the superstructure, and the number of columns that are placed over the mat foundation must be more than 2. So this type of foundation is called, it is mat foundation. Basically, it is used whenever there is the weak soil or the soil whenever there is a condition that the understrata soil of the site are unable to carry the load coming from the superstructure, meaning whenever there is low bearing capacity of soil. So here there is some examples of the mud or raft foundations. There are different types of mud foundations. Here, the first one is the mud foundation that is without beam or without stiffeners. So here, this is the mud foundation, which comprises only the columns and excludes the beams. Here we don't have any beams or we don't have any stiffener here. So the second types of mud foundation is the mud slab with some drops or some thickening slab here, because here there may be higher punching effect here at under the location of every column. So in order to uh, resist the higher induced shear or punching effect under every column, we need to provide drops. And the other is, the mat foundation with beams or with a stiffener here. We have a stiffener in X and in Y direction. So those stiffeners will provide more stiffness to the mat slab in order to resist the higher soil pressure which will be induced under the mat slab here. So those are the three most common types of the mud foundation which are being used in our country. So basically, this type of foundation is being used in our country, and all the rest, this kind of foundation are usually used in other countries, that is out of Ethiopia. And the other types of foundation it is a deep foundation which transfers load mostly by end-bearing and friction from the weak strata of soil to the hard strata of the soil at a greater depth. So we need to go down to the soil until we get the good or hard strata of the soil. So in order to get a good strata, or in order to get an adequate soil having adequate bearing capacity resistance, which can carry the load coming from the superstructure. So we need to use a deep foundation. So there will not be a possibility of settlement because the foundation or uh, the load coming from the superstructures are transferred to the hard strata, which protects the problem of settlement. And usually applicable for high weight structure. That means for higher structural load, it is applicable. It is advisable to use a deeper foundation. So we should not use a shallow foundation for structure having higher structural loads. If we use shallow foundation for structure having higher structural load, so will lead to the problem of settlement. And it is strong against lateral loads. Basically, high-rise buildings are liable to the higher lateral loads such as winds and earthquakes. So, in order to provide higher resistance against lateral loads, we need to provide deep foundation. So, some of the example of deep foundations are caissons, piers, and pile foundations are some of the examples of the foundation. So so what does Kaizen mean, and what does pier mean, and what does pile foundation mean? So basically, Kaizens are those are nothing. Those are the similar to piers, but basically recommended for the bridges that are located under or just along the rivers or oceans. And the pier is basically used for bridges. And the pile foundation is basically used in a place where there is no water. So the difference between pile and pier is, pier is used in for bridges, and piles are used for structures that are located under the rivers. And piles are those are structures that are used out of the water. So those piles are basically just maybe boarded pile or just maybe driven pile. So boarded piles are nothing but those are the cast in situ pile, and driven piles are those are nothing but precast piles. So the deep foundation it is costly because it uses more sophisticated work methodology, and it is also complex because it uses a piling machine and the shootcrete machine and also the anchoring machine. So it is more or less it is mechanized system. And this type of foundation is basically recommended for high-rise structure having higher structural loads, where there is a need of getting hard strata. So, for example, suppose if the allowable bearing capacity of the soil is, it is suppose if it is 100 kilopascal at the foundation depth of maybe 3 meters, and when you go down, the bearing capacity of the soil will be increased. So, at 10 meter, for example, at 10 meter, the allowable bearing capacity of the soil may be 380 80 kilopascal. So the structural load coming from the superstructure maybe suppose if it is 300,000 kilonewton. So this much amount of superstructure load will not be resisted by the soil having 100 kilopascal. So what we are going to do, we need to go down until we'll get the good strata of soil. So we may go down up to 10 meters and we'll get 380 kilopascal. And even this much amount of bearing capacity of soil may not be adequate to withstand this 300,000 kilonewton load. So we need to go down until we'll get a good strata also. That is a higher hard strata. So maybe we may go down an extra of 10 meters. So how much it is? 23 meters. So here we may have hard rock here, for example. So basically hard rocks have the bearing capacity around it is 300, which is greater than 300 kp. So the soil or the hard rock having the allowable bearing capacity greater than 600 kilopascal may be adequate enough to withstand this 300,000 kilonewton superstructure load. So in this case, we need to provide a pile foundation having a length of that is 23 meters, for example. In this case, that is 3 meters, 10, 10, that is 23 meters. So we need the total length of our pile maybe that is 23 meters. So we should not, excavate the soil in bulk up to 23 meters because it is costly. So instead, we need to provide the pile foundation. So pile foundation is it is costly and it is complex. So we'll see it in the other tutorials for the deep foundation in detail. So the type of the foundation is, it is Kaizen foundation used for bridge as a pier in water. That is, in water structure, it is recommended to use the Kaizen foundation. It is a precast concrete structure because it is impossible to use cast in situ concrete in water. Here support, this is a water, and here this is a bridge, and this is the Kaizen. This is the Kaizen, and here this is the shafts or the of the Kaizen here, meaning when we see the just this Kaizen in detail, it looks like this one. Here we may have an axial load coming from the deck here, and this is the diameter of the Kaizen here, and here this is the depth of the Kaizen or the depth of the foundation here. So this the wider contact area will provide higher resistance for soil pressure here. And the other deep foundation is, it is bored pile, or what you call it is cast in situ pile. So it is a deep foundation used in higher structural load condition. It is constructed in a cast in situ techniques under the ground, meaning the bored piles are nothing but thus transfers the load from the superstructure to the soil by using the end bring and the side friction methods. So the bearing the pile capacity here, this is the pile capacity. See the pile capacity, that is the maximum load that the pile can carry, which is equal to, that is QB, the end bring capacity. That means the capacity of the pile under its base plus the capacity of the pile at its surface. That is what we call it. It is side friction. So the friction or the side frictional resistance of the pile plus the end bearing capacity of the pile, what it gives, it is the pile capacity. So the bored pile can transfer the load by using side friction and end bearing mechanism. Here, this is the types of the bored pile. Here we may have end bearing pile. So the pile will be called end bearing if and only if the majority parts of the columnar load can be resisted by the end bearing parts of this pile. And the pile will be called the friction pile if and only if the columnar load is resisted by the side frictions. That means the majority parts of, if the majority parts of the columnar load is resisted by the side friction of this pile, so the pile will be called side friction pile. If the majority parts of the columnar load coming from the superstructure is resisted by the end bearing parts of the pile, so the pile will be called end bearing pile. And here we have also the tension pile. Here the direction of friction is in upward direction in the case of friction pile, and the direction of friction or force will be here down in the case of tension pile. So we may have three types of bored pile. That means end bearing pile, friction pile, and the tension pile. So the surface frictional resistance or the capacity of bored pile equals to, that means here this one. Here the side frictional resistance of the bored pile equals to half of the side frictional resistance of the driven pile. So we will see it later, because the driven piles are more stronger than that of the bored pile. And the other is here just we have a video which shows what does bored pile mean. Here just we can watch this video. Here there is the auger beads which extracts the soil from the pit, now here there is here this is the excavation of the pile. Just after removing the soil, the reinforcements of the pile will be inserted, and after that the concrete will be casted. Here, the reinforcements are inserted, and the concrete is casted here. So the superstructure continued. So this type of pile foundation is called, it is bored pile foundation. And the other is the other types of deep foundation, or the other types of pile foundation is, it is Derival pile foundation. So Derival pile foundation is nothing but it is a precast pile foundation. So it is a deep foundation used in high structural load condition. It is constructed outside the ground, meaning the pile may be prepared at the production site and transported to the construction site and will be inserted into the ground by using a hammering method. So in the case of derivative pile, the capacity of the derivative pile equals to the end-bearing capacity of the derivative pile plus the side frictional resistance of the derivative pile, which is similar to that of the bored pile. And we will see it in later tutorial in detail. Here, this is, the end-bearing pile, and this is the friction pile, and this is the tension pile. So, with reference to the derivative pile. Here, if the majority parts of the superstructure is resisted by the end-bearing parts of this driven pile, so the pile will be called end-bearing pile. If the majority parts of the columnar load is resisted by the side friction, so the driven pile is called, it is side friction pile. If the majority parts of the columnar load coming from the superstructure is resisted by the side friction, but the direction is in downward direction, that means which is parallel to the direction of the columnar load, that the pile will be called the tension pile. And here we have a video just to show what derivative pile means and how the work methodology will be applied during the execution of the derivative pile. Just see the video. Here, this is, the machine, and it hammers the precast piles into the ground. So here there is a hammering effect. Now the pile is going down until it arrives at the depth of the pile foundation bed. Just like this. So here, it arrives at its bed. So the pile cap and the construction of the superstructures continues. So these types of pile is called, it is a derivative pile. So here the this strata maybe it is hard soil, or the layer which is adequate enough to withstand the load coming from the high-rise buildings. So here there are some pictures shows the arrangements of the piles here. This is the arrangements of the pile foundation. Here this is a single pile with a pile cap here. This is pile cap, and this is the pile. And here we have two pile here. This pile may be derivative, or this may be bored pile. And here we have also three pile. In the case of three pile, we may have a triangular pile cap here, and we may have a rectangular pile cap here, because here we have four piles here. And in the case of this one, we may have 5 piles. One is at the center and the other is at the corner. And in the case of this one here, we have 3 piles here. We have 3 piles in this direction. And so all those are the arrangements of the pipe. So the number of pipes depends on the magnitude of the columnar load coming from the superstructure. If the columnar load coming from the superstructure exceeds the capacity of the pipe, so we need to provide a higher number of piles, which is more than 1 pile. So the number of piles depends on the capacity of the pile plus the amount of the structural load coming from the superstructure. And the other is the soil pressure under foundation. So in shallow and deep foundation, there is an induced soil pressure. So this soil pressure is called, it is the reaction of the superstructure load. So we may have 2 types of pressure, that is gross soil pressure and net soil pressure. So in the case of gross soil pressure, it is the total soil pressure which includes pressure due to columnar load, pressure due to sulfate of footing, and pressure due to sulfate of soil from ground level to foundation level. So this what we call this gross soil pressure. So gross soil pressure is, it is nothing but here the load of the backfill soil plus the load of the sulfate of the footing plus the load coming from the superstructure, that is PC. So PC plus that is PC over A, because we are calculating the gross soil pressure, that is gross soil pressure, which equals to PC over the area of the footing plus gamma of the soil times depth of the soil. But ds is nothing but this one. This is what we call, it is ds. That is the depth of the soil, the backfill soil, plus gamma of the concrete times the thickness of the footing. So this is what you call, this gross soil pressure. So this gross soil pressure should not exceed the allowable bearing capacity of the soil, that is Q allowable. So such kind of soil pressure is called, it is gross soil pressure. And the next types of soil pressure is the second types of soil pressure is, it is net soil pressure. So net soil pressure is nothing but it is the total soil pressure which does not include sulfate of footing, sulfate of soil from ground level to the foundation level. Here net soil pressure consists only pressure due to columnar load. So the net soil pressure, that is Q net, equals to P, that is the columnar load over the area of the footing. This is what we call, it is the net soil pressure. So the net soil pressure is nothing but that is the reaction. This net pressure is called, it is the reaction. It is the reaction of PC over A. This one. So this soil pressure equal to PC over A. So we will exclude the sulfate of the footing and we will exclude the sulfate of the backfill material. So these types of pressure is called net soil pressure. So when we use the gross soil pressure and when we use the net soil pressure. So the next explanation will answer the question. So the area of the footing is calculated based on the criteria of gross soil pressure, not exceeding the safe bearing capacity of the soil. The bending moment and shear strength in concrete footing are calculated based on the net soil pressure. So be take care here. So the size of the footing can be calculated based on the gross soil pressure. And the this what you call it is a serviceability limit state requirement. This is serviceability limit state. For serviceability limit state requirement, we need to use the gross soil pressure. And for strength, that means for ultimate limit state requirement, we need to use net soil pressure. So we need to avoid considering the weight due to backfill material and the weight due to the sulfate of the foundation during the calculation of bending moment and shear strength. So if we include or if we consider the sulfate of the foundation and the backfill material, so the our design will not be economical. So it incurs an extra thickness of foundation as well as it uh, incurs an extra uh, area of reinforcement. So we need to be economical during the design of the foundation. So we need to use net soil pressure for ultimate limit state requirement, and we need to use gross soil pressure for serviceability limit state requirements. And this is for deflections and for just calculation of soil pressure and for just checking the crack and all the serviceability limit state requirements will be depends on the gross soil pressure. And here there is also a distribution of soil pressure under foundation. So suppose there is an overhang on all ends of the combined footing here. Suppose this may be combined footing or this may be mat foundation. So we may provide an overhang here on the left of here. We may use an overhang here or we may use an overhang here. So just overhangs are provided on two directions here. There is an overhang on all ends. So the distribution of the soil pressure under the footing is just looks like this one because here we have rectangular combined footing or rectangular mat foundation here just like this. So here this is the center of mass of the footing. This one is the center of mass. So the distance from here up to here is what? Suppose this one is it is L over to here, and the distance from here up to here is L over to here. So the location of the resultant force and the location of the center of mass matches here. In this case, the distribution of the soil pressure is rectangular because there is no eccentricity. E equals to 0, meaning that is P times E, which is equal to 0. So there is no any eccentricity moment. So whenever there is no an eccentric movement, so the distribution of the soil pressure is rectangular. So during the design of this mat foundation or this combined footing, so we need to just convert this soil pressure, that means this soil pressure into to the uniformly distributed load per every strips. Here, suppose this is the footing here. So here we may have a column here or we may have a column here. So we need to divide the column into we need to divide the footing into column strips and the middle strip. And after that we can convert here. This is the width of suppose this is the width of if this is the width of here, this is B width of the column and strip here. So we need to here this is W. So W multiplied with the width of the strips, and it provides what the line load. So this So the line load will be applied at the strips. So we can design our strip as a beam, as a beam. So this is, the concepts behind the design of the mat foundation. So we need to use a strip method in the case of conventional rigid method, or ultimate, we can use the finite element analysis method. So both of them will be providing, closer results. And the other is, there is an overhang on one end, meaning there is an eccentricity on the here. This column is located at the edges of the footing, and here there is some overhang here. So here XR is nothing but it is the distance between the center of force of Q1 and the center of mass of here this one. So uh, here in this case, the location of the resultant force and the location of the center of mass matches to each other. So that means E equals to what? 0. So in this case also we have a rectangular distribution of soil pressure. And the other is there is no overhang onto indices, meaning whenever there is eccentricity. So here there is the location of the resultant force here and the location of the center of mass of the footing here is different. This is the center of mass of the footing. So for this one. And here this one is it is the center of rigidity of the foundation or the location of the resultant force. So there is an eccentricity E in this direction. So in the direction where there is an eccentricity, then there will be maximum soil pressure here. So there will be a significant variable soil pressure distribution here. So significant variable linear soil pressure distribution will be observed in this condition. So this there will be Q mean here and there will be Q max here. So how can we calculate Q max and Q mean? So Q max and Q mean can be calculated using the flexure formula, that is the Q, which is equal to P. P is nothing but it is the total column load over the area plus that is the eccentric moment, that is mx times y over ix, that is the moment of inertia about the centroidal axis of the foundation, plus that is my times x over iy. So ix and iy are the moment of inertia of the foundation with reference to the centroidal axis. And mx and my are the eccentric moment about the centroidal axis of the foundation. And y and x are the location of the point here. The location of the point with reference to the centroidal, the center of the foundation. So this is the flexure formula that can be used to calculate the soil pressure at any point. So here this is plus or minus, or this is plus or minus, because there may be the clockwise direction or the clockwise movement can be considered as positive, and the anti-clockwise movement can be considered as negative. So keeping this side convention, just we can calculate the soil pressure, that is Q mean and Q max at any points of mat or combined footing, or that is rectangular footing foundation. And there is also a uniaxial or biaxial centric footing, that is columns are located at the centroid of the footing. That is footing with movements in x and in y directions. That means there is an induced x and y. Here, When the eccentricity E is less than L over 6, that means here the eccentricity, the location of eccentricity is within two-thirds of the length of the foundation or the width of the foundation. So in this case, there is a trapezoidal soil pressure distribution under the footing here. So this is basically advisable. You know, this kinds of soil pressure distribution is applicable for the design of foundation. So we have P here and we have the eccentric moment M here. So this moment induces eccentricity E on the right side. So if this distance is within two-thirds of the length of or the width of the pile from the foundation from the center of the column, so in that case, the distribution looks like this one. Here we have Q max and here we'll have Q min. So Q max will be recorded on the direction of eccentricity because there is a reversible movement here in this direction. So, and the other, this is when eccentricity is less than L over 6. That means within two-thirds. So for the length and width of the foundation. And the other is when E is greater or equal to L over 6. So the soil pressure distribution like this one, here this one. It starts at this point and just it goes linearly in significant variable magnitude. So we'll have Q max here. So the Q max here, the Q max will be positive. That is the convention of the sign is it is compression. Compression can be considered that it is positive, and it acts in upward direction. And after this point, you know, in this direction, there will be here. This is compression. That is compressive. That's compressive stress here. And in the case of this one here, there is, you know, this one is it is in tension. So tensile stress under the soil is not advisable for foundation design. So we need to exclude this area, the area which is on the left of this point. So we need to exclude this area and we need to increase the area of the foundation by this magnitude because this is ineffective area. So there will be, you know, uplift problem here. That means the footing and the soils are not in contact way. That means there is no contact surface between the foundation and the soil. So this tension zone must be considered during the design of the foundation. And here the distance from this point up to this point can be calculated based on a given equation. Okay. So what is the distance from this point? So that means from the corner closer to the eccentricity to the point where the soil pressure becomes zero. So this distance can be calculated based on the following equation. Here points of zero soil pressure can be calculated by using this equation. That means the distance from this point up to this point is that is ED. I mean maybe this distance is suppose this is x. This is x. So x equals to 3 into that is width of the foundation or length of the foundation over 2 minus ED. So ED is the eccentricity distance. So if the eccentricity that is ED is suppose that is eccentricity, if eccentricity ED equals to L over 6, for example. If it is all L over 6, so you can substitute L over 6 here. L over 6, so L over, I mean, so this one is L over 6 here. You can substitute ED by L over 6. So L over 6 or BF over 6, just to make similar this and this. Then this one is 2 over, 2 over 6 minus 1 over 6. That is BF. And this one is BF. How much is it? 1 over 6 BF. 1 over 6 BF. So times 3. Times 3. This one. So BF over 2. So x equals what? X equals to BF over 2. So this point will be at this point. So the soil pressure distribution looks like this one. Suppose this is the column and this is the footing. So the soil pressure distribution looks like this. The soil pressure distribution will be 0 at the center of the column and will be maximum at the corner closer to the eccentric distance. So this is the general formula to calculate the distance between the zero soil pressure and the maximum soil pressure. And here, this is the general formula. Basically, the soil pressure at any point, we have already said before, this one. This is, the flexure formula. And if there is a movement mx and mz, an extra movement due to the lateral load, so in that case, we need to add this extra moment into the eccentric movement, so that we can calculate the soil pressure at any point. The distribution of soil pressure under combined and isolated footing. Here, if there is an offset geometrical arrangement of the column with reference to the footing, that means if there is a AX or AY, but AX and EY are the geometrical eccentricity, not the load eccentricity. Here, this column is located at some distance, that is X, along in this direction. Here, then the stress distribution looks like this one here. So, in this case, EX greater than L over 6 or less than L over 6 or equals to L over 6. Which one is correct? That is, it is within two thirds. So X is less than L over what? 6. This one. In this case, because it is trapezoidal distribution here. And whenever there is an eccentric distance along in x direction, keeping that there is no any eccentric arrangements along the y direction, so the stress distribution like this one, that is trapezoidal soil pressure distribution along the x direction will be observed here, just like this. And the other is when ED equals to L over 6, that is just here. This E is not the structural eccentricity, is not the load eccentricity, but rather it is the geometry eccentricity. So if this column is located, E equals to L over 6, so the distribution of the soil pressure looks like this one. So there will be zero soil pressure here and maximum soil pressure here. And when there is the geometrical eccentricity of the column with reference to the column, the footing is greater than L over 6, that means just like this. So the pressure distribution look like this one. So the soil pressure will be 0 at the center and maximum at the edge. This is a uniaxial. This one is this and this and this are a uniaxial. Directional offset. That is the offset in x or in y direction only. But whenever there is an offset in y and in x direction, that is bidirectional offset. the stress distribution looks like this one. That is, there is centricity EY in this direction and AX in this direction. So the this shaded area shows the stress distribution. So there will be maximum here and there will be minimum here. So this one is the maximum soil pressure here, and this one is the zero soil pressure. And here, when we go into this direction and when we go from this to this direction, the soil pressure distribution will be increased. So the distribution of soil pressure under mat or raft foundation also looks like this one. Just here, previously I have already said the distribution of soil pressure under the combined footing, which is the concepts are similar here just. So this is all about for today. Thank you very much. If you like my video, don't forget sharing all my videos to your friends so that your friends will be getting more relevant tutorials with reference to the detailed the modeling, analysis, and designing of high-rise building structure based on the European and Ethiopian building codes or standard. So if you are not a new member, don't forget also subscribe my channel. If you subscribe my channel, you will be getting more and more tutorials that have already been prepared and tutorials that will be also prepared for the few in the future with reference to the designing of high-rise building and steel structure based on the Ethiopian and European building code of standard. And if you want to receive also an immediate notification, just you can press the bell icon. So if you have any questions, commenters, don't hesitate providing me in my comment box so that I will be answering your comments and your questions within a short period of time as much as possible. So this is all about for today's tutorials, which is the basic concepts and principles that we are going to follow during the design of a foundation. And this is the tutorial part 28. So next time I will be showing you the detailed modeling, analysis, and designing of mat foundation of the previously modeled, analyzed, and designed theory building. So based on the concepts that we have already discussed today. So see you next time. Bye bye.